Hey honor students, day 25 video here for looking at tension and pulleys. We're going to figure out what's going on with those pulleys you've been looking at in class the last like 2 weeks. So to give you an idea, this is to give you an idea of what's going on in Newton's laws and how to deal with complex situations like pulleys. I'm also going to introduce your next force to you. So far we talked about imbalance, which is also called net force. We've talked about weight, which is mass times gravity. We've talked about normal force. We've talked about friction, which is mu times normal force. And now we're going to discuss tension. So your classwork notebooks are out. We're going to begin, like always. You're going to pause, rewind, make sure it makes sense. We don't have enough time in class to go over everything in depth. That's what these videos are here for, and that's why you're awesome. So tension is a force. Tension is just a force due to a string or rope. So if something's connected by a string or rope and it's making a force on it, we know there's tension involved. Like all forces, tension is measured in newtons. And what's really unique is one string will always have the same tension on it throughout. So imagine like a tug-of-war between a bunch of people, like at the pep rally. Even though one side may be pulling a lot more than the other, the tension's the same throughout the string. Their extra force is being transmitted to the other people, but the string does not have one section on which is more tension than the other. It's the same tension throughout, measured in newtons. This is one of our two situations we're going to be dealing with. A pulley that's completely vertical. It's called an Atwood machine. Please copy this picture down as best you can. Label masses M1 and M2. I'll wait. We're going to assume that this is a massless pulley with no friction and the string has no mass as well. We're going to do that because in reality, the bigger this object is mass-wise, as you could probably imagine, the more force it takes to move. And taking that force means you get less motion for these objects. Long story short, part of the imbalance between these two is making this thing move. And we don't want to factor that in because it's really kind of tough. If you take AP Physics 1 with me next year, which you should, my senior years, will take it in college and report back to me, you can start developing into that. It's actually pretty neat. But right now, let's make it simple. Let's say there's no mass on the pulley itself. The string has no mass. The only masses are the actual hanging things. And just for today, let's assume that in this specific case, M1 is heavier than M2. So which way will M1 move? Yeah, down. Which way will M2 move? Up. Does it matter if M1 is super high versus super low? Does the height make a difference here in terms of their imbalances? The answer is no way. The height does not make a difference. The only thing that matters are the forces on them. It also doesn't matter if somehow you gave it a push and M1 was moving up at first. Once you stop pushing the system, since M1's heavier, it is going to have more force down than the other force balancing it, so it will eventually move down. What we're about to do is we're about to make free body diagrams for both M1 and M2. Since they're two separate things, we'll make two separate pictures, and then eventually relate them using our ideas. Doing so, like we did in class the last 2 days, is to give you a good understanding of what I expect from you. We're going to draw a free body diagram for each. Now, in the past, students from a bunch of different classes had trouble with this. But by the way you've been learning, I think you're to get it pretty well, just like you've done last quarter. Let's start off with M1. Can you please draw a free body diagram of M1 as best you can? And start by asking yourself, what is it touching? Well, what is it touching? Just the string. And which way is the string pulling it, or pushing it, up or down? Nice, the string is pulling it up. So we're going to have an up force from the string called tension. There's no normal force or friction because there's no surface touching M1, only the string is. Hey, what force does not need to touch in order to be felt? And the answer is weight. Which way is weight? Down. Long story short, the string is pulling it up, the weight is pulling it down. What about M2? Can you try to draw a picture now? All right. What is M2 touching? The string again? The string's pulling it up, but its weight's pulling it down. You have pretty much the same picture. The only difference is that the weights are different because the masses are different. Notice I'm keeping the pictures separate. Please do that. I didn't want to show that. I'm screwing myself up. Now let's circle them and say which way the imbalance is. If M1's heavier, which way will it speed up? Up or down? Down. So let's say the imbalance is down and positive is down, because positive is always which way the imbalance is. What about for M2? Which way is the imbalance there? Good. The imbalance is up because M2 is going to speed up. Now for some conceptual questions before we do the math. Which is more, the tension or the weight of M1? This is pure logic. Here's how I want you to think. Which has more force, the weight down or the tension? And the answer, the weight down for this one, because it's speeding up downward. Or in other words, if there's an imbalance, this weight has way more force than this tension. The weight of M1 is larger since the imbalance is down, and the weight of M1 has to be larger than tension to make an imbalance down. Okay. Which is more then, the tension or the weight of M2? Since the imbalance is up, the tension's got to be more. You have to have more tension pulling up than weight pulling down. Cool. So now we're going to solve for it. Let's create net force equations for this picture directly underneath it. Which of these two forces is positive? Weight of M1. Which one's negative? The tension. And they equal an imbalance. So weight 1, positive, minus the tension, which is negative, that's why it's minus, equals the imbalance. Newton's second law says imbalance is ma. I put m1 in because that's the mass we're looking at. And weight is mass times gravity, m1 times gravity. But Jock, isn't gravity always negative? No! Gravity is down. In this case, down is positive. We don't include the negative in there. Plus, if we said downward is negative, we would actually put the negative in front of the whole thing and just leave gravity as positive. Negative does not mean a mathematical negative. This means direction. So for example, tension, we're not going to put a negative value in for tension. We just simply said tension is negative because up is negative. That's what the whole point of it is. Look over here. Can you please show me your rock by trying to create the net force equation, as you're going to have to do in class in a slightly different situation? Okay, you're back. Here's how you should have done it. The tension is up. Up is now positive because that's the way the imbalance is. This is now negative. So tension minus weight 2 equals imbalance. Tension minus m2g, again, g here is positive because the whole negative part of its weight is in front. And then mass is m2. I'm going to teach you in class how you can take these two equations, set them kind of equal to each other, and solve for acceleration and tension and get actual values with masses. That's more of a math thing, though, and I'd rather have that in class with you than explain over a video. Although if you ask me to, I'll make another video of it just for your sake. And finally, we're going to see how these basic pictures and forces and these equations can be made in any different situation. You're not going to be memorizing this stuff. You're simply going to be asking the questions I ask you about what's it touching, which way is the imbalance, and then creating these new things and showing that even if I give you a situation like the Earth going around the sun, you know what's going on with the physics. You could solve for it and figure out what's happening. And that makes you not mathematicians, but physicists. I look forward to seeing you on our next class. Have yourself a wonderful time.